Okay, so now let's start the second lecture by Aaron Brown on stationary measures for discrete random dynamical systems. Please.
Okay, so I'll continue my mini course. So I want to do two separate topics today. So first I want to state some theorems from papers with myself and co-authors, some of whom are in the audience. And I also want to state how I think of this Zariski density and get some dynamical properties of this. So I'll start by stating some theorems. But before I state the theorems, let me give some setup. So the space that we're going to work on is the 2 torus, which R2 mod Z2. And before I perturb, I'm going to start with a linear random walk. So let me take A1 up through AK in SL2Z. And throughout, I'm going to assume that this group generated by this finite list of matrices is Zariski dense, whatever that means. And I'll give you better ways to think of it that's equivalent in dimension 2. So assume this is Zariski dense. And I'll give you an explicit example in just a minute. Okay, I guess I'm going to tell you right now, following my notes, how I think of Zariski density in 2 dimensions. So in dimension 2, a group being Zariski dense, I think is equivalent, and certainly all the dynamical things I want out of it will be equivalent to saying that gamma is not compact and strongly irreducible. Okay, so I've replaced one definition with another definition. Strongly irreducible. And so what does strongly irreducible mean? It means that if I take a proper subspace of the linear action, so this group is a group of matrices, it acts on R2. So this just means that for all one-dimensional proper subspaces, E inside of R2, so I don't want the ambient R2 or the zero-dimensional subspace, but for every proper subspace, the orbit gamma hit E, so matrices act on subspaces, gamma and gamma, this is an infinite orbit. So there are no one-dimensional subspaces that have a finite orbit. And I think in dimension 2 that should be equivalent to Zariski density. And this is maybe a little bit more linear algebraic way to think of this criterion. And if you know Furstenberg's theorem, this looks familiar. And one explicit example you can just take, if you want, we can just take 2 matrices. So we could take 2, 1, 1, 1, and we could take maybe a friend of it. So A2 is 3, 1, 2, 1. Does that have determinant 1? So 3 minus 2 is 1. And these are both hyperbolic, and they don't commute, and so they'll generate a Zariski dense subgroup. So you can just take these 2 matrices for the rest of today. And I'm going to take M to be the Lebesgue measure on the 2 torus. And I'm going to tell you two sets of theorems. The first is the conservative perturbations. Conservative perturbations. So what am I going to do is I have my linear random walk generated by matrices. I'm going to take small perturbations, not of the group action, but just of the generators. So let's take F1 up through Fk. These will be C2 diffeomorphisms. So they are in the space of C2 diffeomorphisms of T2. But I want them to be perturbations of the matrices I started with, so I want them C1 close. And so I'll let, but I want, before I say that, I want to say something else about these. So not only are they arbitrary diffeomorphisms, but they are M preserving. Diffeos. So I'm working in the conservative case. I fix a background volume form. I'm going to look at volume preserving perturbations. So now I'll let epsilon be some way of measuring how far these are away from what I started with, so how far they are in the C1 topology. So the minimum of the C1 distance, and I don't really care, I only care about the topology. I don't care how you define C1 distances. You can do it in charts. The C1 distance between the ith nonlinear generator and the ith linear generator. So I think of this as a diffeomorphism of the torus. This is a diffeomorphism of the torus. Ask how close they are in the C1 topology. 1 less than I less than k. And of course, you can just think of k equals 2 in just these two examples, these two matrices. And when we set epsilon equal to 2, we exactly get the Benoit-Quat setting. But I want to work with positive epsilon. And now I'll let mu, so before mu was a measure on SL2Z, now I want to let mu be a measure on my perturbed generators. And just for simplicity, I'll take it to be evenly weighted. So let's take it to be 1. The minimum. Oh, probably I mean the maximum. Okay, thank you. Okay, too many Caparinas. Okay, thank you, Pavel. Okay, so mu is 1 over k, the sum of Dirac mass at the ith generator, I from 1 to k. So there are k different maps. Just put even weights on all of them. Or if you like, there's no reason that you have to have even weights. You could just take sum of a probability vector at the fi and the only thing is that you want to make sure that you give positive charge to each of the perturbations. The epsilon that will work in the theorem will depend on the probability vector a little bit. So there's no reason that you need equal weights. And then in this setting, definition, so there are two measures. There's a measure that drives our random dynamics, and then there's another measure on the space that we're acting. So nu on T2 is mu stationary if, when I act on it by this random dynamics, it's a fixed point. And so this will mean that nu is equal to the sum of fi star of nu, but this sum is now, this has mass k, this has mass 1, so they can't be equal, so then we have to average. And so here I'm just averaging by k, or you can average by the probability vector if you want to do the more general. And now, same question, if we take the setting of the Benoit-Quat theorem and we perturb the generators, what can we say? So here's a theorem of myself and Federico Rodriguez-Hertz from a paper from 2017, but the theorem I'm going to write down doesn't appear anywhere in the paper. It follows from all the proofs, but it needed a little bit more cleaning up, and so some cleaning up was done by a student of Alex Eskin named Brian Chung, and his paper, he never published it, but it's on the archive from 20. So for conservative perturbations, what we can say is for epsilon positive but sufficiently small, so we want all of the generators to be reasonably close to what we started with. The size of the epsilon will depend on sort of the weights, and it will also depend on the matrices you started with. But for epsilon sufficiently small, 1, we have some sort of rigidity, which says the only ergodic mu stationary probability measures are, exactly as in the Benoit-Quant theorem, they're either finitely supported, so they're just sitting on some finite orbit of this mysterious nonlinear action, if I can spell it though, finitely supported, or, well, there's another stationary measure, which is this invariant measure that I assume that all of the generators preserved. Or it's the Lebesgue measure, M. And now we assumed that Lebesgue measure was invariant. Finitely supported stationary measures are also always invariant, so then we get stiffness. So every stationary measure is actually invariant by the whole group. I won't formulate it again because I formulated all these on yesterday. 3, we get that orbits are either finite or dense. And you can also get the equidistribution. So every orbit is either finite or it equidistributes. Equidistributes to this invariant Lebesgue measure. So the proof of Benoit-Quant, it's a very dynamical proof, but it heavily uses the fact that these are linear maps and it's an affine random walk. And somehow the conclusion is open in the conservative case under C1 perturbations of the generators. There's a question, though.
What do you mean by ergodic?
What do I mean by ergodic? Yeah, so I didn't quite define this, but invariant measures form a, what is that called? A convex simplex. Stationary measures also are convex. They form a simplex. Ergodic just means the extreme points. And so you can define it in terms of invariant things should be null or co-null, but you can also just think of it as the extreme points of the simplex. So it's not a convex combination of two other stationary measures. It's an extreme point. Because you could be some combination of a finite thing and the Lebesgue measure. So let's just only look at the extreme cases. Okay, so Federico and I were pretty happy when we proved what goes into this theorem. But then we really wanted to do something in the dissipative case, and we couldn't do anything in the dissipative case. And probably the reason is that in 2017, I was the junior person on the project. But now I guess I'm a senior person, and I have junior collaborators. So with the junior collaborators, we were able to do something in the dissipative case. So see. I'll need a little bit of setup. So dissipative perturbations. And so again, now suppose, Ian likes my funny word, suppose. Suppose F1 up through Fk, they are possibly not M preserving. So we're not working in the conservative setting anymore, and we'll let epsilon be the max, again, of the C1 distance between Fi and Ai. And what we'll let mu just take it to be the evenly weighted driving measure, so delta Fi, I from 1 to k. And now the question is, what are the mu stationary probabilities? And what I want to emphasize in this case is that you should expect something different than what happens in the conservative world. In particular, in the conservative world, there was a special measure, the Lebesgue measure, that we assumed was invariant under all the generators. Here, we're not assuming that. And in fact, what we want to show in the end is that there's an absolutely continuous stationary measure, but it won't be invariant under the generators. And you can build examples with no smooth or absolutely continuous gamma mu invariant probability measure. And so, for example, you could take F1 to be my A1, which was 2, 1, 1, 1. You could take F2 to be a C1 perturbation of 3, 1, 2, 1. We'll assume that F2 preserves the origin, has the same fixed point as this matrix. And then we'll assume, I think, the determinant of the derivative at 0 is I think it's enough just to say that this thing is different from 1. And so then F1, so these are anosoph, the anosophness is open. F1 has a unique, absolutely continuous invariant measure, has an absolutely continuous invariant probability. And F2 has no even absolutely continuous invariant probability measure. And this you can just do by, because it's an anosoph map, you can use Lifshitz and argue, I think, that this guy has no invariant, absolutely continuous probability measure. So the group generated by here has no invariant measure that's in the measure class that's invariant under the whole group action. So you definitely don't expect this stiffness. Okay, but then what were we able to do? So this is L, so this is with myself, Homan Lee, Davi Obata, who's in the audience, and if you have technical questions, you can ask Davi, and Yuping Ron. And so again, for epsilon positive, but still sufficiently small, every ergodic mu stationary probability measure, I'll call it nu, is either, so we could still have potentially some finite sets for this group action. So it's a finitely supported. But if it's not finitely supported, then it has to be as good as possible in the first conclusion in the conservative case. So the other option is that it is absolutely continuous with respect to the ambient volume form. So i.e., nu is absolutely continuous with respect to the Lebesgue measure. And so this is the theorem, really the second bullet point that I want to talk about on Thursday and Friday, is how do we show some strange measure with some that happens to not be finitely supported, happens to be absolutely continuous. And in this setting, you can get various corollaries. Yes? So yeah, because if we perturb from affine, you can get fully supported. And if you work really hard, we're going to work in the L2 topology, so we're going to build some sort of L2 density. If you work harder, you can probably even get a smooth density, but I won't worry about that. But my notes are over here. So I think, yeah, as a consequence of this, we can also get, orbits are finite or dense. And I think we get an equidistribution as well. But maybe one philosophy that I like about this theorem is that finitely supported things, they're sitting on, it's a finite set, that has dimension 0. Any measure that's absolutely continuous, even with a terrible density with respect to Lebesgue, has full dimension. So this has Hausdorff dimension 2. And what this is saying is that there's no invariant objects, there's no invariant fractal objects. So somehow we started with a big group, we perturbed the generators, and we still have no invariant or stationary fractal objects. So this is really sort of how I think of selling this kind of theorem. Corollary is that there are no fractal objects for this group action. And I know Balázs is going to try to convince us that fractal things are nice, but I hopefully at least gave you some justification for why you might want to rule out fractal things. And this is that kind of theorem along that line. Okay, so these are the two main theorems, and this is the one that I'll talk about on Thursday and Friday. But now I want to go back to the linear world, unless there's questions at this point. I think in this case, so we also show that it exists, so it always exists, and I think in this case it's unique. Yeah. So now I'll shift gears, and I'll talk about sort of how I think of dynamical consequences of Zariski density. So again, let's take AI in SL2Z, but actually everything I'm going to say for the short period, actually mostly it all will work in SLDR as well. So you don't need the integer coefficients, you don't need the dimension. And I'll take mu to be, maybe I'll let myself put a probability vector on the matrices, so there's k of them. If you want, just take p to be 1 over k. Pi is positive, and the sum of the pi's is 1. And let's suppose that this group generated by the AIs is not compact and is strongly irreducible. And in 2 dimensions, this is equivalent to it being Zariski dense, I think. But let's just keep this as our standing hypotheses. So theorem, due to Furstenberg will appear a lot for the rest of today, tells you that when you take the IID random product of these matrices, the norm grows exponentially fast with the same rate, and so this is that you have a positive Lyapunov exponent. So Furstenberg says that if I take one of these matrices, I'm going to index it by I0. So I grab the 0th matrix, IID, and I multiply it by the first matrix chosen IID, and I multiply it, and I want to do n of them, so the last one will be indexed by n minus 1. And I ask, what is the norm of this thing? I want this thing to be exponentially large, so I'll take the log of it. I'll take 1 over n, and this is going to converge to something that's going to converge to a lambda. Lambda is positive, so there exists a lambda positive, which is independent of the sequence, and the norms of these products converge to this. Okay, but I need one more quantifier, so this is for mu to the n, almost every random path chosen IID through the matrices. For nu to the n, almost every choice of indices, I0, I1, I2, etc. And certainly people at IMPA who have taken classes with Marcelo, I'm sure know this theorem. It's definitely in Marcelo's book. And one way to prove it is using what's called the invariance principle. But there's a little bit more structure that comes out of Furstenberg. Not only do you get this positive Lyapunov exponent, but you actually get something that sort of witnesses it. So there exists a mu stationary probability measure. I'll call it nu superscript f on RP1. So RP1 is the space of lines in R2. So this is the projectivization of R2 with the following property. Okay. That sees the Lyapunov exponent. So lambda is the integral of log of A restricted to E. Let's see, d nu f of E. So let me just write it down and then say some words about it. And then I need one more integral here, which is d mu of A. Okay, so this is a measure on projective space. And so it eats one-dimensional subspaces. I can take my matrix, I can restrict it to a one-dimensional subspace and ask what is the norm of that thing. That's just a number. I could take the norm of that, I could take the log, and what the Furstenberg measure, so this is called the Furstenberg measure, what the Furstenberg measure does is it sort of witnesses the top Lyapunov exponent. So all the norm growth comes from, for each generator, you see what it does on relative to this measure, and then you average over elements of the generator. And one remark is that nu f is stationary, but not invariant, which again, if you know what the invariance principle is, you kind of know why it can't be invariant. And so what does it look like? So RP1 looks like this. This measure is probably some sort of Cantor measure. It probably is not the Lebesgue measure. And so it's some sort of measure. It's going to have positive dimension, but it's some sort of Cantor set-like measure. When I act by a generator, it probably takes the measure and it's going to contract it into some region. So now I need some colors. So maybe A1 of the measure, and here I'm being a bit sloppy. So A1 is a matrix that acts on R2, but then it naturally acts on lines in R2. So I'm looking at the induced action on projective space. There's some other measure called, there's some other image, A2 of this Furstenberg measure, and probably A1 of the Furstenberg measure is different from the Furstenberg measure, and the image under A2 is also different. But when I average this measure and this measure together, I get back what I started with. And so the 1/2 A1 of this thing plus 1/2 A2 of this strange measure gives you back the measure. And how do you build this thing? So I won't prove the building, but I'll give a construction, and then this construction we'll want to use a generalization of it later. So fix an E, some one-dimensional subspace in real projective space. So RP1. And now I'm going to do something funny. I'm studying the random dynamics, so things are indexed by futures, but I'm actually going to index things by pasts here just because indexing by past makes some sense to me. So I'm going to take delta mass at, let's see, the last one I want to do is AI minus 1. The next one I want to do, so this is the last map I pick. Then I want to do AI minus 2. And I want the last one to be AI minus n. So it's a little bit strange that I'm indexing by negative numbers, but ignore that. They're going to be chosen IID, so it doesn't really matter how I index them. And I'm going to apply this to the direction E. And now I started with the direction E, and now this is pointing in some other direction, depending on multiplying all these matrices together. And so then what I'm going to do is I'm going to integrate d mu, and so mu to the n, but I'm going to pick these matrices IID, and I'm going to average them all together. So of all these past indices. So I minus 1, I minus 2, I minus 3, up to I minus n. So over here, at time 0 or step 0, I pick some subspace E. At step 1, maybe I have two subspaces depending on the two places where this E could go under the two matrices. So this is A2 of E, and this is A1 of E. And then at step 2, maybe I have 4 dots corresponding to the 4 possible ways that I could have chosen these things. And as I keep going, this measure is going to it's always going to be a finitely supported measure, but it's going to have more and more atoms with less and less mass because of the averaging, and it's going to look more and more like a fractal measure, like some sort of Cantor set. And let me call this nu sub E n, and sort of the one way to build the Furstenberg measure is to say that nu E n, this is going to converge to the Furstenberg measure. And it's going to be independent of the initial mass that it took, the initial subspace I picked. And so it actually kind of converges independent and even sort of uniformly in the choice of the set E, or of the initial point E. And actually, you don't even need to start with a point. You could put any probability density you want on here, and then just push that probability density around using all the random compositions, and it still will converge to the Furstenberg measure. And sort of a corollary of this is some sort of finite time version of hyperbolicity. It says for every vector v in R2 with norm 1, I take my vector and I start doing random matrices applied to it. And I'll do n of them. So this matrix might have this n, nth power of power or product of n matrices might have a contracting direction. And so this vector might be norm much, much smaller than 1, because this might point in the sort of the stable singular direction for this matrix. But what I want to do, well, if I want to take the norm and I want to take the log of it, what I really want is this thing to be positive. So I want v to grow, so I want the log to be positive. But the log might be negative if v is pointing in the stable singular direction. So what I'm going to do is I'm going to average over all possible matrices here. So I integrate d mu to the n of the indices, so I0 up through in minus 1. And I haven't said anything, I've just told you an object. So you take any vector that you want, and you multiply it by a bunch of matrices, you average over all the possible products, and you take the log, and this thing you can make as close to the Lyapunov exponent as you want. You can make it lambda over 2. And one thing I left out, so for every v, I left out one quantifier, which is how many of these matrices you do you need to pick. So there exists a single n, maybe at least one, so that no matter what vector you plug in, when you take the random product under all possible matrices and average together, on average you see exponential growth. So it might be that this points in a direction that contracts, but that's exponentially very, very unlikely. And because of the strong irreducibility, no matter what vector I pick, it will be in the unstable direction for most of these products. And so it will expand exponentially, and on average, you'll always see expansion. And this property is going to come back over and over again, either at the end of today or at the beginning of Monday, or beginning of what? Thursday. So I want to see this first in the linear setting. Okay, and I want to say two more things about Furstenberg measure, but maybe other questions at this point? Hopefully I haven't said anything that's too nonsense either. So here's a fact, is that this Furstenberg measure is always going to have a nice Hausdorff dimension, and it's always positive. But you can actually say more than just positive dimension. So this measure has what's called a Frossman property. And as far as I know, this is due to Guivarch. Maybe in this two-dimensional setting it's due to someone else, but the general setting is due to Guivarch. And so, okay, but what I want to put a bullet point here to emphasize this is some sort of notion of transversality. Transversality, which is going to appear as some sort of non-concentration. So here's a theorem. I'm not exactly sure who to attribute it to, but I think the most general version of this was due to Guivarch. Where does the apostrophe go? Does it go there? So there exists an alpha positive and a C positive, maybe C bigger than 1, such that this measure is either is Frossman or is C alpha Holder. So C alpha Holder. Or sometimes this is called the Frossman property. And I'll tell you what C alpha Holder means in a minute, but this is if you're C alpha Holder, you know you have dimension at least alpha. This is something much stronger than just having some Hausdorff dimension. So what does C alpha Holder mean? It means that for all E prime in RP1, so this is a measure on projective space. So pick a point and look very, very close to that point and ask how much of the measure is concentrated there. So let's take the ball of radius r centered at E prime. So this is the ball of radius r, and let's measure that ball. So if this was an atom, this thing wouldn't change. If this was an atom supported at E prime, it wouldn't change. Or if it had multiple atoms and one of the atoms gave positive mass to E prime, we would see no decay. So we want to definitely have no atoms. What we want is that this thing decays, and it decays in R. So it's less than C, R to the alpha. And so what is the picture here? This is RP1. I pick any direction I want. What is the reasonable distance should be the angle. So I look in the ball of radius R, or the angle. I look angle R to the left and R to the right, and I want the amount of mass in here to decay like, like R to some power. And the point is that the C and the alpha is uniform over all directions. So if you're out of the support of the mass, so maybe, maybe this arc here has 0 measure, then it still works here. So E prime, if I look at this ball and E prime is out of the support of the measure, then the new F of a ball of radius R at E prime is equal to 0. Okay, I don't know why I drew that in the middle of the picture. Nu F of a ball of radius R at E prime. This is equal to 0, so it's easy to decay if you're away from the support. So this is only interesting if you're in the support, and this is some sort of uniform decay of the measure uniformly in every neighborhood of any point. And in fact, if you want to prove this kind of thing, when you want to prove Frossman properties, you usually prove it about measures that are limits of approximations, and you prove an approximate Frossman property. And we have approximations over here, and I'm doing this for the linear case because I'm going to wave my hands in the nonlinear case, but say we can do a similar thing. But in fact, for every E prime in RP1, I can look at the ball of radius R centered at E prime, and I could take its, what is my notation? Subscript E. I could take the nth approximation to this measure and ask how much mass does this charge the ball of radius R at E prime. And this is still going to be less than C R to the alpha. So for all E prime and also for all E, this will be true. And now people should be very upset. So are the students upset yet? I need a student to be upset. It's this one that I built over here. Maybe equals this guy. This measure has lots and lots of atoms. It has probably 2 to the n atoms. Can measures with atoms have any decay? Once you get, if E prime is in the support of this, then you'd see no decay. So this is completely nonsense, but it's true as long as my R is not too small. And this is sort of for all R that are not too small, but they can be exponentially small. So for E to the minus beta n. And let's see, maybe if I called, probably E to the n. Yeah, you can hide the exponents wherever you want, but I think if I do it this way, that's the right way to do it. So as long as you're not looking on too small of a scale, your balls are not too concentrated for the approximating measures, and then you can pass this to the limit. And every proof I know of a Frossman property, you prove it for the approximating things and then pass it to the limit.
So a similar lower bound for these inequalities asks too much, right? The other way. The two sides are not comparable.
Oh, the lower bound? I don't want a lower bound. I only care about the upper bound. I only care that this measure doesn't get too concentrated, and that the non-concentration is polynomial. Okay, when am I stopping?
We have 6 minutes.
6 minutes, okay. So I want to leave the world of linear random walks but I haven't changed my title yet because I want to use things from the linear random walk. But first I want to give a definition. So the dimension of my manifold is 2. If you want, the manifold is always just the 2 torus. I have mu. Let's take it finitely supported. On this group of C2 diffeomorphisms of M. Again, if you want more general, you can put some moment conditions, but let's just have it be finitely supported. We say mu, or the random walk determined by mu, is uniformly expanding, or expanding on average, but I think in our paper we're calling it uniformly expanding. And I'll emphasize in the future, and then this will be too much to write, so eventually I'll call this UEF, if something happens. Okay, and what is the something that happens? So there's some quantifiers here, but first, let me take a diffeomorphism, let me take its derivative at some point, and then plug in a vector. So I want to say, for all x in M, and for all vectors that are unit tangent vectors at x. And you imagine that you pick a random point, a random diffeomorphism, and a random vector. If you apply that vector to a diffeomorphism, you expect that vector to get bigger, unless you're extremely unlucky and it points in the stable direction of f. So let's take the norm of this thing, let's take the log of this thing, and ask this to be positive. But of course, you could have picked your x and your f and your v very badly and put this in the stable direction of a hyperbolic object f. And so, but let's do this on average. Let's pick the f randomly and let's average what happens. So average d mu to the n, maybe just power n of f. Okay, there's some missing quantifiers, so what do I want? I want that this thing is positive, so bigger than some c. And so what I want is that if there exists some uniform c and some uniform n, such that no matter what point I start at, no matter what vector I pick, when I look at the random walk of length n starting at x applied to v, these vectors grow on average. And that looks very similar to what I'm about to race over here. I'm just going to rewrite it slightly differently. I.e., if what? If mu is 1 over k, sum of delta masses at fi, I from 1 to k, then we're integrating log norm the derivative at x of some arbitrary random product. So fi0, fi naught, and this is just d mu to the n of the indices chosen IID. And this thing we want positive, and oh, sorry, I'm not sure why I'm integrating. Let's just do this thing. We want this positive, and let's just sum over all indices I0 up through in minus 1, and divide by probably k to the n. So this is just averaging over all possible. Let me finish the expression, though. We average over all possible futures, the vector v, and we want this thing to be positive. And there's also uniform expansion in the past, where we replace f by f inverse. So maybe I'll write it down again on Thursday. But then let me finish with just one punchline. Note, this property, uniform expansion in the future and uniform expansion in the past, they are open in the C1 topology on the maps that I'm charging, that I'm generating my random walk by, and the weak star topology on the driving measure. And why is that? Because if I C1 perturb by f's, my generating things, this is a continuous function. And if I perturb my measure, I'm integrating a continuous function, and so that's the definition of the weak star topology. And so the consequence is that by starting with this group of matrices being Zariski dense, this is going to force that sort of the linear random walk is going to have uniform expansion in the future and uniform expansion in the past. And then this is going to force our non-linear random walk. Even if we perturb the weights on our generators a little bit, has this property: the uniform expansion in the future and the uniform expansion in the past. Okay, and so I'll stop there. So yeah, that's it for today. And then Thursday, I'll try to say how we use these things, but I've already shown you in the linear case the information that these properties get for us. Okay.
Thank you very much.